Welcome to part one of the Earth Science lecture series and looking at the nature of our solar system. And what I want to do today is cover a substantial amount of slides. There's about, I think, 64 slides in this presentation, but about 30% of them are some really nice pictures of how we view our solar system today. And so we're going to look at the Earth's place in the solar system, and we'll do a little comparison of what the Earth's place is beyond the solar system. We'll look at the evolution of our knowledge of the solar system. In other words, about 1800 years ago, it wasn't believed that the sun, in fact, is in the center of our solar system. So we'll kind of take a tour through what I like to call the big guns of astronomy, who contributed to the knowledge of what we know today. I think it's also important in this discussion to see how the seasons work. There's a lot of misconception out there in terms of what causes the seasons, so we'll explore that. And then there's a series of slides that give a brief description of each one of the planets, and some pretty good pictures of each one of the planets, and we'll look at some of their descriptions. And finally, we'll end up looking at the moon, and we'll look at the moon phases, and we'll look at the eclipses. So to get started, probably what's important here is certainly to look at how distances are measured within our solar system. And we're going to look at this concept of astronomical units, or AUs. And an astronomical unit represents the distance from the sun to the Earth. And that distance, on average, is about 93 million miles. So we would say that 93 million miles is equivalent to one astronomical unit. So if something or somebody says that there's an interstellar object or something in our solar system that is 3 AUs, then we would take 93 million miles, we would multiply it by 3, and we would end up with 279 million miles away. And so the astronomical unit is really confined to the distances within our solar system. Once you move beyond the solar system, you now start talking about light years. And light years, of course, are quite a bit farther than a typical astronomical unit. A light year is how fast light can travel in 1 year. So if you say, okay, well, light travels at 186,000 miles per second, we'll allow that light to travel for that year at that rate of speed, and we would say that it would move around 6 trillion miles. So we would say that 1 light year is approximately about 6 trillion miles. But again, we're going to confine our discussion within our solar system, so we will be mostly using astronomical units. So the next series of slides, I think there's about 6 or 8 of them, 6, 7, 8 of them. The next series of slides ask you a question: how big do you think the Earth is compared with other celestial bodies? And so I'm going to go through a series of pictures. There's really no text written on each one of the slides. It's just pictures. And I want you to get a sense on how big the Earth really is relative to other celestial bodies. So let's go ahead and start with the inner planets, which in this case would be Earth, Venus, Mars, Mercury, and Pluto. And Pluto's included in this particular slide. And I know Pluto's not recognized as a planet, but we're going to include it in this slide. And we can kind of see within the terrestrial planets, within the first 4 planets, that Earth is probably the biggest out of all the terrestrial planets. And you can see Mars, its relative size, and Venus is a close match to Earth in terms of its size and so forth. Let's now take the terrestrial planets and let's compare those to the outer planets. Okay, and so now kind of focus your attention on Earth, which is towards the bottom of your screen. And now we see that Earth gets kind of small really fast. And in fact, you can see that Jupiter would represent the largest planet of our solar system, then Saturn, Uranus, Neptune, and so forth. In fact, they say that you can put 500 Earths into one Jupiter. Now let's take the planets in our solar system and let's compare those to our size of our sun. All right, at this point you should be going, wow, look at that. And so now again you can find Earth, which is now just basically a little dot towards the bottom, and you can see Jupiter got pretty small, and you can see that the sun is actually fairly large when you compare it to the rest of the planets in our solar system. In fact, if you were to weigh the entire solar system and you were able to weigh the sun and the planets along with the sun, you would find that the sun is 99.85% of the entire mass of the solar system. So really, what this does is it kind of allows the planets to be insignificant in terms of gravitational pull. In fact, there's always rumors out there that when the planets at some point align themselves along the elliptical plane and they're all in alignment, there's always rumors and things out there that say that catastrophes are going to happen on Earth because of the pull of all the other planets and so forth. And actually, this is not even true, because again, the sun represents 99% of the solar mass. And so any gravitational pull that Jupiter would have, or any other planets on Earth, would be insignificant compared to the massiveness of the sun. Let's go ahead now and take our sun, and we are now going to compare it to other suns beyond our solar system. And so here now, if you look at the photograph, find our sun, which is on the left-hand side, the smallest sun that you can see there. It says sun right here. And when we compare our sun to other stars, like, for example, Sirius. Sirius is a white dwarf type star, which is pretty much on its way out in terms of the ages of stars and the evolutions of stars. Then you got Pollux, which is a red giant. But look at Arcturus. And Arcturus is considered a huge red giant type star. And typically red giants would be classified as middle-aged type stars in terms of the evolution and age of stars. And you can see that it pretty much dwarfs the size of our sun. So you can kind of see that we're getting smaller and smaller. And in fact, if you look at the bottom of the screen, you find that Earth is basically invisible at this scale. So now we're not done. Let's go ahead and compare these series of stars to other stars that are beyond our solar system. And this slide here now shows you Arcturus, which is down here. And that was the previous large red giant that we looked at in the previous slide. And now you can see that our sun has become a pixel size. And here's another Rigel. Here's another white dwarf. But look at Antares. That is another huge red giant type star. This star here is known as Betelgeuse. And again, Antares. And you can see that it really dwarfs our little star, which our sun is considered a main sequence star. So really, kind of in perspective, we're kind of small when you kind of look at our solar system, our sun, and Earth with respect to the universe and so forth. So a lot of times I'll say in class that you think you're special, but you're really not, because we're very, very small in the scheme of things. However, it was pointed out to me several semesters ago that, in fact, we are very special, because, in fact, that we can exist on such a small planet. So I said, well, okay, you're special. Let's now go back about 1800 years of Earth history. And let's go ahead and follow a timeline or an evolution of what I like to call the contributors to the knowledge of our solar system. So we're going to look at that evolution of our knowledge, and we're going to see how, for example, you today believe that in fact the sun is in the center and the Earth is the third planet. But it really wasn't that way 1,800 years ago. In fact, let's go back to the early Greeks at about 600 BC. And you got to think about a little bit of what types of tools, measurement tools, if you will, that folks had back then to look at the solar system and to look at the observations they make and so forth. And so really back in 600 BC, geometry, math principles, trigonometry was kind of employed, and watching the sun rise in the east and setting in the west. And so based on, again, the mathematics that were available, based on their observation of when the sun rises, Ptolemy, back in 141 AD, Claudius Ptolemy presented what is known as the geocentric model. And really, geo means earth, centric means center. So Ptolemy presented an earth-centered solar system, where Earth is in the center of the solar system, and all the other celestial bodies in terms of the planets, other planets, and the sun revolve around the Earth. In fact, Ptolemy was so adamant that he published a article called an Alchemist, 141 AD, to the science world. And actually, based on what was available to Ptolemy for observations and so forth, it seems reasonable, right? Even today, we walk outside and it doesn't look like we're really moving. In fact, you could convince yourself that if you didn't know any better, really the sun is moving around the Earth. So one of the things that Ptolemy had to explain, given the geocentric model, was this process called retrograde motion. And even today, when you look in the nighttime sky, retrograde motion exists. And what retrograde motion represents is, if you look at the model here, each one of these stars, or each one of these little patterns here, represent background stars. And in moving in front of the background stars are the celestial planets, Mars, Jupiter, and so forth. And so from Earth's point of view, and like I said, even today this takes place, when you watch Mars, for example, let's use Mars as our example. When you watch Mars, for example, traverse across the night sky, and let's say this is taking place over a month period. So every night you go outside, you look at Mars, and Mars will traverse across the night sky. It'll move over a little bit every night, but then at some point during the month, let's say, Mars will start to appear to move backwards in the night sky. And so Mars begins to move backwards in the night sky for a little while, and then it will regain itself and move forward again. This backwards motion against the background stars is referred to as retrograde motion. So how did then Ptolemy explain retrograde motion using the geocentric model? Well, if you look at the animation, you see Earth as the center of the solar system, and you see Mars. And as Mars revolves and rotates and moves around Earth, Ptolemy hypothesized that all the other planets, including Mars, undergo what we call an epicycle. If you look at my arrow, this is like where has its own little orbit. And as it moves around in its own little epicycle, the viewpoint from Earth, so this blue line is the eyesight line from Earth, so we're looking at it from Earth, it would give the illusion that as Mars traverses through the background of the stars, it would have a backwards motion. So you can see Mars moving backwards in the sky, and then it goes forward again. Let's watch it again. So Earth, looking at Mars, Mars epicycles, Mars gives the appearance that it's moving backwards in the sky and then forward in the sky. And so when you look at all the other planets, they also undergo retrograde motion. And as I said earlier, even today, planets continue to be under retrograde motion. So this is something that Ptolemy had to explain given the geocentric model. So this is just another little diagram showing you the geocentric model. It shows you Earth in the center. It shows Mercury, the Sun, Venus, and so forth and each one of these circles represent the epicycles that Ptolemy assigned to each one of the planets to account for retrograde motion in the geocentric model. Well, I want you to take a look next at this next contributor to the solar system, and this is Nicholas Copernicus. And the first thing I want you to notice is the years. And you notice that Copernicus came on the scene in about 1473. And if you recall, Ptolemy produced his almagest in 141 AD. So that's about 1,500 years difference. And so for 1,500 years, most folks bought into the geocentric model and bought into the epicycles as retrograde motion. So 1,500 years later, Nicholas Copernicus comes on the scene. And Nicholas Copernicus is known as a very articulate mathematician. And he took data and information from the geocentric model and started to notice discrepancies. In other words, Copernicus would look up at the night sky, and based on the geocentric model, Mars should appear in this location. And of course, Mars didn't show up there. So this led Nicholas Copernicus to say, something else must be going on. So Nicholas Copernicus did some more study and concluded that the Earth basically is another planet. So in order to fit his mathematical model to predict the location of planets, he had to modify the geocentric. So he concluded the Earth is another planet. He included that daily motions of the Earth can be explained by a rotating Earth now. So this time the Earth is not motionless, but in fact rotates, creating rising suns in the east and setting suns in the west. And so he developed the heliocentric model, where the sun is now in the center, and used circles as orbital paths for each one of the planets. Now, imagine this. For 1,500 years, the geocentric model was believed. And now here comes this guy and starts to modify it and actually puts Earth just as another planet. The question is, philosophically, from a human standpoint, how well do you think that went over? How well do you think folks bought into that and said, wait a minute, you're telling me that Earth is just another planet? It didn't go over very well at all. In fact, Copernicus was put under house arrest for these statements. This view here is now, this next slide is the Copernican view of the solar system. And again, you can see where heliocentric, sun-centered, and proposed by Copernicus. And you can see the sun now is in the center of the solar system. And now you see Earth as just another planet. So this is now beginning to resemble and look like what we know today in terms of the sun being in the center of our solar system. So one of the things that Copernicus had to do was now he had to explain retrograde motion in the Copernican system, or the heliocentric system. And so the way Copernicus approached it, by leaving the sun in the center, is he says, well, the closer the planet is to the sun, the faster it must move around the sun. So in our example here for retrograde motion in the Copernican model, we see that the Earth, we're going to say this is the Earth, and we're going to see the Earth is rotating around the sun much slower than, of course, Mars. And so really what happens is Earth basically laps Mars as it moves around the sun. So again, if you follow the blue line, so we'll follow the blue line here. So you follow the blue line, which is the eyesight watching Mars, and then we look at Mars compared to the background stars, you can see that Mars will have that appearance of backwards motion. And what's really important here is when you define retrograde motion, the key word is it's the appearance of backwards motion. Because if you look at what really is happening is Mars is not moving backwards. In fact, Earth and Mars are moving around the sun in the same direction. And so again, the viewpoint then gives you the illusion or the appearance of the planet moving backwards. And so even today, as I explained, it happens today with planets. And so one can watch other planets in the night sky, and they will start to show retrograde motion, but still moving in the same direction. So we're going to let you watch this one more time. Here it goes. Okay, so along comes another main contributor to the evolution and knowledge of our solar system, and this is Tycho Brahe. And again, notice the years. In this case, it's the 1546 to 1601. And Copernicus in the previous slide was in the 1400s. And of course, Ptolemy was about 1500 years earlier in, I think it was 141 AD. The point that I'm making is, notice how knowledge of the solar system is starting to gain faster and faster. In fact, we have a small time interval between Tycho Brahe and Nicholas Copernicus. And so Tycho was able to design and build what they call pointers that accurately predict the positions of the planets in the night sky. But based on the design of those pointers, Tycho didn't really believe and buy into the heliocentric models because he says, according to his pointers, that the background stars should be shifting every 6 months. So think about this. If the sun is in the center and you have Earth, for example, on one side of the sun, and then 6 months later, Earth is going to be on the other side of the sun, then it would be logical that the background stars would show a shift. But in fact, they didn't show a shift with Tycho's pointers. And so he said, well, based on that, I don't believe that there is a heliocentric model. However, the pointers actually brought out another concept, and this is known as the stellar parallax concept. And this tells you, well, I do a demonstration in class called the thumb demonstration. So I'm going to try and talk that demonstration, and you follow along. So we're going to pretend that your nose is going to be the sun. And then your left eye will be the Earth in one position. And then 6 months later, your right eye will be Earth in another position. So what I'd like you to do is take your thumb and put it in the hitchhiking position. And hold your thumb out in front of your face with both eyes open. Now, with both eyes open, put your thumb in the middle of your nose with both eyes open. Then close one eye, look at the position of your thumb. Close the other eye, look at the position of your thumb. And without moving your thumb, what is happening as you alternate between both eyes? What you should notice is your thumb is shifting back and forth. All right, now take your thumb with your arm stretched all the way out and pull it closer to your thumb, pull your thumb closer to your nose. And now go back and forth between your eyes. And what you find is the closer your thumb is to your nose, the bigger the shift. The farther your thumb is from your nose, the smaller the shift. And so now what I would like you to do is stretch your arm all the way out and then move your thumb about 50 feet away from your nose. Now, of course, you can't do that because you need a 50-foot arm. But if you were allowed to do that, what would happen to the shift of your thumb if you got farther and farther away from your nose? The shift would get smaller and smaller and smaller. So what Tycho didn't realize, the reason why the background stars weren't shifting when it goes from 6 months around the sun to another 6 months, is because the background stars are so far away. And so they are so far away that the shift is negligible. You're not going to see it. And so he may not have bought into the heliocentric model, but what he did show with his pointers, that again, the background stars are far far, far away. In fact, during the time of Tycho and Copernicus, and especially during Ptolemy, it was believed that when you looked at the stars, you should be able to go up to the mountaintop and be able to touch a star. And of course, we don't believe that today because we've been conditioned and we've been taught that the background stars are far, far away. So in our brains, we already know they're far away. But if you didn't know that, then in their day, you would get the illusion that you could in fact touch the star. So Tycho Brahe's design of the pointer was very instrumental in learning that the background stars are, wow, way the heck out there. And so this slide here is just another example of interstellar parallax. And here you have the sun, you have the Earth in this position. 6 months later, the Earth is in that position. You watch the star, you should be getting a parallax, you should be getting a displacement, but you don't. So in my analogy earlier, the sun would be your nose here. This would be your right eye. This would be your left eye. This would be your thumb. So you can kind of work with that analogy and try and put in your own words what the stellar parallax concept means. And again, this is just another slide showing you the interstellar parallax concept. Okay, let's now move into Johannes Kepler. And again, look at the time span, 1571 to 1630. So again, what do you notice about the gaining of knowledge? It's starting to increase very rapidly, starting to move very fast. Again, you had Ptolemy, you had Copernicus, and right after Copernicus, Tycho, and then right after Tycho, you have Kepler. And so Kepler took both Copernicus and Tycho's data. And again, Johannes Kepler was a very, very meticulous mathematician. When you say 19.2, Kepler would say 19.23456. So he was very accurate, very meticulous, had a very mathematical mind. And what he showed was that although Nicholas Copernicus was very close to the heliocentric model, Johannes Kepler, who is considered actually the birth of modern astronomy, tweaked or modified the concept of Copernicus to really accurately show and define exactly how the planets are moving and where they are located. And so Johannes Kepler proposed what we call the 3 laws of planetary motion. And it took him basically 10 years of mathematical computing to get these laws to work and to be able to accurately predict where planets lie today. In fact, the 3 laws of planetary motion are used today when designing satellites, when putting spacecraft into the solar system to land on other planets and so forth. So these are very important laws. And so we're going to go over each one of the laws of planetary motion. Kepler's first law of planetary motion is the law of ellipses, where all planets follow an elliptical orbit around the sun. Now remember, Copernicus proposed circular orbits, but again, to make the prediction of planets and how they move more accurate, Kepler then says, no, they're not circular orbits, but instead they are elliptical orbits. And so certainly in the picture you can see here, you can see the planet moving around the sun in an ellipse. And just to make sure we're on the same playing field, an ellipse represents basically a stretched out circle. Now you'll notice in this diagram also that they have the sun not quite in the center, which is true. But in this particular slide, it's not to scale. The sun is just slightly off center. Kepler's second law of planetary motion is known as the law of equal areas. And really what the second law says is the closer the planet is to the sun, the faster that planet will sweep around the sun. And when it moves away from the sun, it's slower. And so you can look at the animation below, and you can certainly see that as the planet gets near the sun, it sweeps a lot faster. as it moves away from the sun, it sweeps a lot slower. Now, the way this second law of equal areas work is let's pretend, or not pretend, but let's say we know that each one of these shaded areas of the orbit field are the exact same volume, or area, I should say. And so this area is equal to this area, that area is equal to this area, and so forth. And so what Kepler had to do, Kepler had to say, well, if it takes the Earth, for example, 365 days to get around the sun once, which is pretty consistent, with the exception of leap year, we catch up every 4 years. But if we take pretty consistently 365 days for the Earth to get around the sun, and yet the sun is slightly off-centered, how do we allow the Earth to be consistent yearly around? Well, if you allow if this area where my arrow is the same as this area where my arrow is, then when the planet is moving and sweeping across this area, it's got to slow down, doesn't it? Because that's a shorter span right there. But when it moves across this area, as it's closer to Earth, it has to move a little bit faster. And that's where we get the fact that the planet sweeps around faster, closer to the sun, and slows down farther from the sun. Now, McDonald's, believe it or not, the hamburger place, practices this concept. My kid and I once were in McDonald's, and we went in to get a soda, and McDonald's person said, hey, all sodas are the same. They're $1 for any size. And my kid says, well, I'm getting a large. So he got a large, and I didn't need that much soda. And so I basically got a medium soda. Cups look different, don't they? So we were sitting at the table, and I started looking at his large and looking at my medium. And I said, wait a minute. I'll bet you the amount of soda in your large fits in my medium. And sure enough, we filled his large up to the brim, and we poured it into my medium-sized cup, and it fit perfectly. In other words, McDonald's is even practicing the Kepler's second law of motion, because in this case, the volumes are the same. And if you notice, the McDonald's medium and the McDonald's large cups definitely look different. The cup certainly looks larger, but in fact, it's really not. In fact, this would be, where you look at my arrow, this would be the large cup, and this would be the medium cup if you look at my arrow. So I thought that was kind of comical that Ronald McDonald also knows about Kepler's second law of planetary motion. And here's another animation or photograph showing Kepler's second law, and see if you can observe where the planet is moving faster, closer, slower, farther. So Kepler's third law of planetary motion involves some tricky mathematics. And so I'm just going to read you a quick passage of what Kepler's mind thinks in terms of his math. And Kepler says, the square of any planet's orbital period, which is the sidereal, is proportional to the cube of its mean distance from the sun. Mathematical statement is T is equal to KR to the 3/2, where T is the sidereal period and R is the semi-major axis. So, example, if A is measured in astronomical units, we know what that is, semi-major axis of the Earth's orbit, and the sidereal period in years is how long it takes to get around the sun, then the constant K in mathematical expression for Kepler's third law is equal to 1. And then the mathematical relation becomes T squared is R cubed. So I read that just to give you an idea of, again, how Kepler is thinking. And basically, he's building a ratio to compare how this Earth moves around the sun to the ratio of Mars, for example, or Jupiter, and so forth. And really, what Kepler's third law of planetary motion says, and if you look down in your left-hand bottom part of the screen, the third law really says one can calculate the distance of a planet from the sun. And that's really what the third law figured out. In other words, astronomers and scientists began to learn the order of the planets. And so if you go to the table on your right-hand side, you'll see now that the planets are now put into astronomical units, which is telling you that Mercury is the closest planet to the sun, then Venus, Earth, and of course we see Mars, Jupiter, and Saturn. And of course, Mars is 1 because that is where the comparison is being looked at. So we have the first law, which is ellipses. We have the second law of equal areas. And then Kepler's third law of planetary motion is called actually the law of harmonies. But in this case, also looking for the distance from planet to the sun. So this is another little animation that kind of gives you an idea of how the planets move around the sun. And what you should observe is the closer the planet is to the sun, it's going to move around the sun faster. And then the farther the planet's from the sun, it's going to move around slower. So this kind of gives you an idea, of how our solar system looks over time. This slide here shows the planets stopped, and I put years down in terms of Earth years, how long it takes the planet to move around the sun once. So for example, we come over here to Mercury, and Mercury is closest to the sun, and so it takes it 0.62 Earth years to get around the sun, 0.62 Earth years to get around the sun once. And so it moves, so it goes around the sun twice to Earth one time, basically. So if you want to get older, go live on Mercury because you'll have 2 birthdays. And then over here, if we take Saturn, Saturn takes 29.46 Earth years to get around the sun once. So if you wanted to be younger age-wise on Earth, just go to Saturn because you would get a birthday every 29 years, which would make me about 3 years old on Saturn. So really, this slide puts things in perspective with respect to age, meaning that age truly is relative. So now we have Ptolemy, in which he did the geocentric model. We have Copernicus, the heliocentric model. Tycho developed the pointers and showed interstellar parallax. We've got Johannes Kepler, that certainly defined modern astronomy today, with looking at the 3 laws of planetary motion. And so by the 1500s, in this case 1564, Galileo came on the scene. And by this time, the heliocentric model was strongly supported. And so the geocentric model by this time is kind of merged out. And the greatest contribution to astronomy from Galileo is looking at moving objects. In fact, to look at those moving objects, Galileo discovered the telescope, or produced and made the telescope. So in 1609, he constructed the first telescope, which first time looking through the telescope, it increased the planet's actual size 3 times and up to 30 times, which today, that happens to be a really, really good pair of quality binoculars. And so if you ever get a chance to get a good pair of binoculars, look at the moon, and you'll be amazed at what you can see. You can see the craters, the maria, all different features on the moon. You could imagine what Galileo and other astronomers must have thought for the very first time to look at objects, through a telescope. In fact, Galileo's discoveries, and give kind of a list of discoveries in a nutshell. He discovered Jupiter's moons, 4 of them. There's more moons than 4 of them today, but he certainly discovered there's actually little moons, or moons that now rotate around planets. Discovered the phases or the planets are spheres and not points of light. And so again, today when we look at a planet, it appears to be a point of light, but with the advent of the telescope, it is now spheres. Discovery of the phases of Venus, meaning that Venus moves in the phases very similar to what we view from Earth to the moon. And of course, Venus being the second planet from the sun. Discovered the topography of the moon, meaning the moon's not smooth. I put a little joke here made of cheese, but in fact, it's got craters and maria and so forth. Discovered that the sun has sunspots, leading to the calculation of the sun's rotation. So when you view the sun, given the sunspots, you can see the sun's rotation based on the sunspots. Then finally, Newton, Sir Isaac Newton comes on board. And again, look at the years 1642, 1727. And really what you should be getting a sense of is that when you go from Ptolemy all the way to Sir Isaac Newton and you look at the time frame or the timeline, you find that the knowledge of the solar system is basically exponentially increasing. And this is very, very typical of what the scientific method represents. And remember, when we talked about the scientific method in the very first week of school, we indicated that the more knowledge that is gained and used from other contributors, the faster and faster concepts are created. And so in this case, by 1642, we are now into the heliocentric model. We've got Kepler's three laws of planetary motion. But Kepler couldn't explain why his planetary laws of motion work and why the planets hang around the sun and don't want to leave. And it was Sir Isaac Newton, coined as the greatest genius to ever exist in terms of mathematics and physics. And what Isaac Newton realized, just because of that falling apple, realized that there is a gravitational force. In other words, he realized that smaller bodies are attracted to bigger bodies. And so really, the reason why the planets don't want to leave, because really, if you look at Newton's first law of motion, now this is Newton's first law of motion, says that when something is in motion, it just wants to keep going forever, unless something else acts on it, and the other force acts on it. And so Newton realized that the planets really want to leave their orbital paths, but they can't because of the gravitational attraction of the sun. So what Newton came up with is a universal gravitational theory. And that is, every body in the universe is attracted by every other body, that with a force that's directly proportional to their masses and inversely proportional to the distance between them. And really, what Newton is saying using this universal gravitational theory is that bigger objects attract smaller objects. And if you think about our solar system, you think about the universe in general, I envision all of the celestial bodies and planets in a gravitational limbo. And everything is in some type of equilibrium with respect to how gravity is pulling on it. And so if one system changes, it can upset the whole apple cart, if you will, and disrupt all of the gravitational attractions between the different planets and so forth. So bigger objects attract smaller objects. And so under the universal gravitational theory, Newton has taught us that gravity gets weaker as distance increases. So this is evidenced by the farther you move away from Earth, the Earth's gravitational pull gets less and less. And you've seen films and pictures where people are floating around in their spaceships. Smaller objects are attracted to bigger objects. So in this diagram here, which is not to scale, I show the sun, I show the Earth. Sun is the bigger object, Earth the smaller object. Earth is going to hang around because of the gravitational pull. Likewise, we can put the moon, which is a smaller object than the Earth, and the moon is smaller than the Earth and the sun. And so if you look at this relationship between the sun, Earth, and moon, it's all in a gravitational limbo. And so one can say, well, what happens if the sun, for some reason, grew a little bigger, just got a little bit bigger? What would happen to Earth? Earth would probably have a tendency to move towards the sun. Or what if the sun decreased in size? Then Earth would have a tendency to probably move away from the sun. So the sun is a perfect size, the Earth is a perfect size, and with respect to gravitational attraction, the Earth is on average 93 million miles from the sun. So Newton then says, okay, let's put a little physics and math to show how the gravitational pull works with respect to the sun and the Earth. And Newton says the Earth moves about 30 kilometers per second away from the sun, but the pull of the gravity on the Earth is about 0.5 centimeters. Kind of reminds me of playing tetherball. And so you have the tetherball, which would be like Earth. You have the rope that would be similar to the gravitational pull. And when you hit that tether ball, it is forced to go around the pole because the rope is holding it. And that's very similar and analogous to how the Earth is gravitationally attracted to our sun. So here's our sun. The sun wants to go 18.5 kilometers per second, but it's being pulled by gravity at 0.5 centimeters. So it forces the Earth to have to make its way around the sun and creates a path. My PowerPoint shows a circle, but we know that Kepler says it has to be elliptical.